Okay, good morning, class. Thank you for coming to the classroom. I am physically not here today, but I want to thank you for coming. If you're watching the video online, I will encourage you to come back because you will see your friends and you will see the TA Kent here. So what we are going to do today is that I'm going to speak for 20 minutes, and then I will talk about some concepts. Then I'll pass the time to Kent to give you some examples of the topic that I'm going to talk today. So the lecture today is about Gaussian random variable, or some people call it the normal random variable. It is one of the continuous random variables that we're going to spend a lot of time on in this course. It is also one of the most useful random variables that you can see in the literature. So what is Gaussian random variable? Just like any random variable, the Gaussian random variable has a probability density function, PDF. And in this PDF, it is a little bit complicated. You have an exponential term that has this e to the power minus x minus mu to the power square, and then there is a constant of 2 sigma squared in the denominator. So this is a two-parameter random variable. We say that x is in Gaussian, given these two parameters, mu and sigma square, where mu, as we are going to show, it represents the mean, and sigma square represents the variance. So let's take a look at this equation. It's a little bit complicated. Now, we can ignore this constant for a while, because this constant has nothing to do with your x. So all's happening is about this x minus mu squared divided by 2 sigma squared. So let's look at this equation. This is a quadratic equation, and it is a symmetric equation. That means it is a even function on this x minus mu squared. So what is the center? Well, as you can see here, it is a x minus mu squared, so we should expect something to happen around mu. And we're going to look at this square, and there's a minus, and there's an exponential outside. So whenever we see an exponential to the power minus something, we should expect it to decay in some way. And because this is symmetric, we should expect it to go down like this. The center point of this bell-shaped function is mu, and there is a spread of this bell-shaped function, and the spread is given by this parameter sigma square. There is a constant in front of the Gaussian PDF, and this is 1 over square root 2 pi sigma square. And this constant is there to ensure that if you take the integration of fx dx from minus infinity to plus infinity, this is going to give you 1. And so we need to have this constant. So the shape of this Gaussian random variable, we can see it from two perspectives. One is that how are we going to look at this Gaussian random variable as we change the parameter mu, and what happens if we change the parameter sigma. So if you change the mu, let's say we're looking at this example here, we are moving from minus 3 all the way to 4, then you can imagine that the center of the Gaussian is shifting from the left to the right. If we are changing the sigma, then we are stretching the Gaussian random variable, which is stretching the PDF from a very small value. So here it will be a sigma equals to 0.8, which is a very, very narrow Gaussian, and to a sigma equals to 4, which will become very wide. So in the following 2 slides, I'm going to show you 2 very basic properties of the Gaussian random variable. They are the proof of the mean and the proof of the variance. So you may wonder, why do we want to prove that? Well, my comment is that you need to do it once in your lifetime, because once you have done it, you'll remember how to derive this mean and the variance. So let's look at the mean. The mean, which is the expected value of x. I can show that it is this parameter mu. So how do we do that? As we recall, the expected value of a random variable, it is defined as the integration of x times your fx dx, where the integral goes from minus infinity to plus infinity. So in our case, we have this fx, which is 1 over root 2 pi sigma square e to the power minus x minus mu squared divided by 2 sigma squared. So that is our PDF. So I can substitute this fx into my equation here. Then I will get this e to the power minus x minus mu squared divided by 2 sigma squared. And then there's a constant, of course. Don't forget that there is also an x, which will go to here. So that is our setup. That is a definition of the expectation of a Gaussian random variable. Now, the next step is a very important one. We are going to shift this x minus mu to center as 0 by letting y equals to x minus mu. So this is a substitution where we let y equals to x minus mu, and therefore dy will equals to dx. And because we have substituted y equals to x minus mu, then you can see that my exponential will become e to the power minus y squared divided by 2 sigma squared. And this x will become y plus mu. The constant will, of course, stay as is. So what will happen to here? Well, I have this summation of y and mu, so I can write it as a 2 pi sigma squared integration of y times e minus y squared divided by 2 sigma squared dy from minus infinity to plus infinity, plus 1 over 2 pi sigma squared integration of mu and e minus y squared divided by 2 sigma squared dy, again from minus infinity to infinity. So how do we evaluate these two integrals? It appears that it is just as difficult as the original one. However, let me tell you a trick. This one is actually 0. For the reason being that this is an even function, but when you multiply it with y, this y times e y minus y squared divided by 2 sigma squared, this is an odd function. And therefore, if you integrate this odd function from minus infinity to infinity, this entire thing will equal to 0. And how about this guy? This guy is just the same as mu times integration minus infinity to infinity of 1 over root 2 pi sigma squared e minus y squared divided by 2 sigma squared dy. So I'm just switching the position of this mu and this constant 1 over root 2 pi sigma squared. I just switched the row of these two. Then I'm looking at this integral. This integral, let me tell you, this is 1. It is 1 because you're integrating at the PDF of a Gaussian random variable. In fact, if you integrate the PDF of any random variable, you're going to get 1. And so you will end up having 0 plus mu, and therefore the expected value of x is just mu. Okay, so in this derivation, the reason I'm bringing up is that it shows two very, very important tricks in integration, especially for this course. One is that you're going to look at whether this function is odd and even, something that we mentioned early on in the semester, that this odd function can help you simplify the quantities. The other trick here that we use often in this course is that if we integrate the PDF of a random variable, you're going to get 1. So these two tricks, when you put them together, you can get to this result very easily. Now, how about the variance? Now, to prove the variance, of course, we can do either using this identity of variance of x equals to the expected value of x squared minus mu squared, or you can directly just plug in the definition of the variance, which is the integration of x minus mu squared times your fx dx from minus infinity to infinity. So in this case, in this problem here, we're going to apply the second definition, the same definition as the first one, but we're going to use this one to show the variance. And as you can see in this, the first line, I'm just copying the Gaussian PDF here, and then I have this x minus mu square. Then I'm going to do a substitution. In this case, the substitution is y equals to x minus mu, but I'm not just interested in x minus mu. I also want to take care of the sigma. So I will let x minus mu divided by sigma. So that is the substitution that I'm using here. And so if we take the derivative, dy dx, dy here, then dy will become 1 over sigma times dx. So what it means is that, first of all, I have this x minus mu over sigma, the entire thing square. It will become y square. And this x minus mu square, but don't worry, you also have this sigma square here. There's a sigma here. There's a sigma here. Okay, so there's a sigma here. So let me put a square, and so I want to put also a sigma in the top. Let me see. So I'm going to put square here. There should be a sigma, right? And there is also a dy will equal to 1 over sigma times dx, and therefore you will have a sigma times here. And therefore this sigma will cancel out with the other sigma. And then there is a sigma square over the sigma square. And so these two will cancel out with each other. And so as you can see here, by using this substitution, I can rewrite this very complicated integral into this 1 over root 2 pi. There's a sigma square in the front, and then there is a minus infinity to infinity integration, y square e minus y square divided by 2 dy. So how do we calculate this integral then? Well, this integral, unfortunately, there's no shortcut. We got to use integration by parts. As you can see here, I'm doing this integration by part. I'm dividing it into 2 halves. The first half, it will be minus y times e to the power minus y squared divided by 2, evaluated from minus infinity to infinity. That's going to give you a 0 because the exponential grows a lot faster than your y. And here you have this integral. The integral, it will just be e to the power minus y squared divided by 2. But I'm going to apply the same trick again. This entire thing is a sigma squared times the integration of 1 over root 2 pi e to the power minus y squared divided by 2 dy. And believe it or not, this thing is just 1 because you are integrating the Gaussian PDF. And so you do everything, then ultimately you will only get this sigma square. So we have proved the variance of your Gaussian random variable, which is the sigma square. So after talking about the mean and also the variance of a Gaussian random variable, let me also talk about the CDF of the Gaussian random variable. To talk about the CDF, the Gaussian random variable, and let me introduce one more concept. It's called the standard Gaussian. In the standard Gaussian, we are assuming that the mean is 0 and the variance is 1. This is a very special Gaussian that allows you to do a lot of calculations using a standard Gaussian table. So the expression of the standard Gaussian, as you can imagine, we originally have fx equals to 1 over root 2 pi sigma square e to the power minus x minus mu square divided by 2 sigma square. Let me just let mu equals to 0, sigma equals to 1. Then you will simplify this original Gaussian PDF into this expression. In this Gaussian PDF, I can take the integration, I can take the cumulative sum, which is this integration from minus infinity to a point x. Then I can convert this PDF to the CDF, where this area under the curve up to the point, let's say here, up to the point y, then I can convert this area under the curve into the height. In this case, it will be f evaluated at y. Now, because this is a very special Gaussian random variable, it is a zero mean unit variance Gaussian random variable, we call the CDF as this notation of a phi of x, where phi of x is defined as the integration from minus infinity to x for a standard Gaussian. So let me just recap here. This standard Gaussian CDF, the CDF of standard Gaussian is defined as this phi function. It is this integration from minus infinity to x of this zero mean unit variance Gaussian random variable. Now, if you read textbooks, you will easily find this concept called the error function. This error function is defined as 2 over root pi, and you're integrating from 0 to x and e to the power minus t squared. The error function is related to the standard Gaussian CDF through this expression. You can do this evaluation pretty easily by sitting down and just go through the derivation once. So this is a conversion from the error function to the Gaussian CDF. This is from the Gaussian CDF to the error function. The CDF of an arbitrary Gaussian function can be evaluated using the standard Gaussian CDF in the following way. So if x is a Gaussian random variable distributed according to the mean of mu and variance of the sigma square, then the CDF of this x can be written as in terms of the standard Gaussian. This is the phi function. So you have phi of x minus mu divided by sigma. So why is this the case? Well, we can start with this Gaussian CDF of an arbitrary random variable. So you have this integration from minus infinity to x of your Gaussian, which is 1 over root 2 pi sigma square e to the power minus t minus mu squared divided by 2 sigma squared dt. Now, pay attention that this t is just a dummy variable for this integration. I don't want to mess up with my x. So this is my CDF of this Gaussian random variable. And I'm going to let a substitution. The substitution is y equals to t minus mu divided by sigma, which is the same substitution that we used when we derived the variance of the Gaussian random variable. So if we do that, then we can go back to this integration. This integration is the integration from minus infinity to x. And now I want to change my limit, not x anymore, because if it is x, then x will become y, it will become x minus mu divided by sigma. So you can think of it as this is originally your t, then this is your new variable, which is y equals to this t minus mu divided by sigma. So that is the upper limit. You will change from x to this x minus mu divided by sigma. And how about the stuff inside? The stuff inside, this thing here, t minus mu squared divided by sigma squared, it becomes y squared. And then the sigma squared will be absorbed because your dy will equal to 1 over sigma dt. And so when you do this substitution, you can see that you can end up having this integral. This integral is integrating from minus infinity up to a point, whatever point it is, and then you are evaluating a standard Gaussian PDF. And therefore, this is just your standard Gaussian, which is your phi function. And then the thing that you're going to put in will just be the upper limit. And your upper limit is x minus mu divided by sigma. So as we go back here, we show that the CDF, which is fx, will equal to this one, and equals to that one, and ultimately becomes this, the CDF written in terms of the standard Gaussian CDF, which is this expression that we are looking at. Now, why do we care about this expression? It's because we can then write down this, the probability of a Gaussian random variable very easily. Now, unlike other random variables where, such as an exponential random variable, you can easily evaluate the probability, for Gaussian, there's no closed form expression to evaluate the probability, and therefore we want to use this standard Gaussian as a sort of like a pseudo closed form expression to evaluate the probability.
So for example, in this case, I'm looking at the random variable x between a and b. Then I know that this is the CDF evaluated at b minus the CDF evaluated at a. And so the CDF of this Gaussian can be written as this standard Gaussian, b minus mu divided by sigma. This is the standard Gaussian a minus mu divided by sigma. So I can evaluate this probability. There are other properties of the Gaussian random variable, including these. For example, phi of y equals to 1 minus this phi of minus y. Probability of x bigger than equals to b is 1 minus the phi of b minus mu divided by sigma, and the last one. So for all these properties, corollaries, you can prove it by yourself. Now, for Gaussian random variables, let me also introduce two more new concepts, which would be very useful as you look at data analysis. So far, we have been talking about the first moment, which is the expectation. It's also called the mean. And then we were looking at the variance, which is the second moment. For Gaussian random variable, I will also introduce two other high-order terms. One is called the skewness, which is the expectation of x minus mu divided by sigma by sigma to the power 3. We call it the skewness. And then the last one is called the kurtosis. And this quantity is the fourth moment. So what are the skewness and the kurtosis? How can they be useful? The skewness is measuring how asymmetrical is your distribution. So an example here would be that if you look at a symmetric distribution like this one, the black one in the middle, you will have a 0 skewness. Just like your Gaussian, you have a 0 skewness. If you have a positive skewness, then you are shifting to, your mass is concentrated on the left-hand side. Whereas if you have a negative skewness, then your mass will be concentrated on the right-hand side. So that can be a very useful quantity as you evaluate your data sets, as you're looking at how asymmetrical your data set is. So that will give you some quantity, some measure of the distribution. Kurtosis is another very useful tool. That is measure how heavy tail is your distribution relative to a Gaussian. So Gaussian has a kurtosis of 3, and sometimes people just calculate the excess kurtosis by subtracting this 3, so that the Gaussian will have a 0 excess kurtosis. So by looking at this diagram, what can we say? Well, if you look at the black one, this is a Gaussian, and so you have an excess kurtosis of equals to 0. You will have a heavy tail, for example, the blue one, when your kurtosis is negative. So this is a heavy tail case. All right, so you have more mass distributed at the tail of this Gaussian distribution. If your kurtosis is bigger than 0, then you have this orange curve, which is a narrower Gaussian. So this table gives you a summary of various random variables, including the discrete random variable and also the continuous random variables. I provide you the mean, I provide you the variance, with the understanding that this Pn, lambda, a, and b, they are the parameters of your random variable. I also provide you the skewness, and I also provide you the excess kurtosis, which are the first 4 moments of a random variable. So the following example is a real data set. It's a Titanic data set. I will give the time to our TA, Kent, to go through this data set with you and to show you some insights that you can draw from this data set. This data set is taken from this website called thekaggle.com. It's a very useful website. You can download a lot of data sets from this website. Many of them, they come with Python codes that you can download and try. So I would highly encourage you to take a look at this website and just register and download some of these data sets and play it out. So the plan for the following 20 minutes or so will be the following. Ken will be here. He will talk about this particular example, give you some insight of how do we analyze the data. And then he will also go through some of the example problems that you are likely going to see in your homework exercises. So thank you for watching. I will prepare the next video, and then and I hope to see you very soon. Thank you.
Hello, welcome to the second half of the lecture on chapter 4.7. We had an issue with the recording, and we're going to make this one to substitute what we said in lecture. We start with the example of the Titanic. So here we can read that on April 15th in 1912, the Titanic sank after hitting an iceberg, and it killed 1,502 people out of the 2,224 passengers and crew. So 100 years later, we are analyzing the data of these poor people, and there's a data set available on kaggle.com, which is a data science data set. We've got a bunch of different data sets on there. Some information they include are the identities themselves, age, gender, and some other demographic information. If we look at the statistics of two groups, the groups of people who died and the groups of people who survived, we can see that the mean and standard deviation are actually almost the same. And when you, and this is of the age. So you look at the age, you compute the mean and standard deviation, you get almost the same values. You look at the other moments, you look at skewness and excess kurtosis, and they are different, very clearly different, especially kurtosis. You can see that one is even the opposite sign of the other. When we do something like this, if we were to just report the mean and standard deviation, implicit in that assumption is that we're using a model of a Gaussian to represent the data. We're going to look at the actual data on the next slide. So we have a mean and standard deviation. Those are almost identical, but skewness and kurtosis can tell the difference. What you'd really like is you'd like to know what is the difference between the histogram on the left and the histogram on the right. It's not always clear how you can report that in a single number, and or what summary of the histogram is going to be different when you compare the two quantities. What's interesting to note is that if you were just to report the mean and standard deviation, that would mean you're implicitly using a Gaussian to model your data. And so what you're doing is you're saying you've got some Gaussian. We've got some Gaussian. My drawing's not perfect, but if we imagine that these are almost the same or identical, then these are just to represent the data. So these are modeling assumptions. So if only mean and sigma, then implicitly Gaussian. But this data is not Gaussian. So this is not actually Gaussian. But we don't really care in a way, because models are tools, right? We're not saying they're actually truth. They're just like a hammer, and a hammer is not true or false. A hammer is just a tool. So even though our data is not actually Gaussian, we can still use it as a powerful tool to understand the data. So then here's a question for you to think about. If we knew the data was actually Gaussian, would the skewness and kurtosis, would they be the same? Would they be unequal? Think about that maybe for a second. Okay, so the answer is that skewness and kurtosis would be identical if we knew that the data, or approximately identical, if we knew the data was actually from a Gaussian distribution. You might even start thinking about other moments too. So we just said if known to be Gaussian, then the skew and kurtosis would match. Okay. Let's talk about the origin of the Gaussian. Where does it come from? Why are they so popular? Why do they have a bell shape? So Gaussians, I think, come from some very old time. I think it might have even been from someone named Laplace, potentially, who came up with Gaussians. And so there was another aristocrat or education person back in the day, and their name was Gauss, and they did a lot of math stuff. But I think Laplace actually came up with the Gaussian. So you should fact check me, but that's a common misnomer, or classically misattributed work. Okay, so then, but what does it physically come from? That's what this one is. So it physically comes from the sum of many independent random variables, and the result is a Gaussian. So the sum. That's known as the central limit theorem. So the theorem applies to any random variable. That's why it's so useful. So any random variable. And as a technical detail, we want to emphasize something we'll look at later, is that summing random variables is equivalent to convolving the PDFs. And you convolve PDFs infinite limited times, you yield a bell shape. And so that's how you get this intuition that the central limit theorem is true. This is kind of like the proof mechanism for the central limit theorem. So one way to show you this is true is just to run some simulation studies. We've got our single sample with the histogram x1 on the top left. If you sum two dice and you plot their histogram for some number of trials, you end up getting the histogram on the top right. You sum 5, you get something that looks a little bit more bell-like. And then in the bottom right, you get something that looks a lot like a bell when you start adding 100 of them together. You also notice that the peaks, right? Like it becomes a little bit, the bins become much skinnier too, because we're taking more values. So two rectangles give a triangle. So we say that the sum of x and y is equal to the convolution of their PDFs. So this is the PDFs. It's kind of nice because earlier we saw how you have to do this trick where you have to do this, dx, right, and you have to use this as a function of y or whatever variable. But here we can get z is equal to x plus y. You can get f of z just as the convolution of their two PDFs, which is really nice. Now you don't have to worry about the CDF stuff. I do think minor detail. So how does this work? Maybe you remember if you've been in your other coursework where you've got your two squares. So say this is the filter, and then maybe this is the signal. So you do the flip and shift. So we'll take some examples through time. Imagine we've just flipped this, and now we're running it this direction. And you see we've got this much intersection. So we're going to make a plot, a stick that's maybe this tall. It continues in time. Now you've got maybe more of a overlap. Maybe the stick is taller now. So we'll draw this arrow like this arrow like this. And then as it continues in time, maybe we've got complete overlap now. So the stick will be very tall. And now you're maybe overlapping the same for a while. And then eventually you'll get to the left-hand side. You'll start decaying bit by bit. So now you see that this is a little bit more smooth than what it was before, which gives you some idea about why this bell shape happens for convolution. So to build intuition, we should think about what happens when you take things to extremes. It's a good practice in life just to see what happens. You will never do infinitely many things. No one thinks you'll do infinitely many things. That doesn't make this pointless. It doesn't make it silly. The purpose of this is to just build a concept about why what we say is true is true. So here we've got the Fourier domain. We know that if you take the convolution of a set of functions, and then you end up, so this is like you've got x multiple times. So you're doing x plus x plus x. And it's not the same. So this would be like x1, x2, x3. This is not equal to n times x, just as a side note. This is not the same thing. So n would be like some value greater than, or it doesn't have to be greater than 0, just some real number. Or here it would actually be an integer, wouldn't it? But it's not the same. No, because these are different random variables. This is the same one multiplied by a constant. Okay, so in the Fourier domain, you've got this Fourier transform of these convolved PDFs. We know from like the basics of Fourier transforms, you can do the multiplication instead. Given this multiplication, what will end up looking like? And so we can take, so this is the, I think this is the rect Fourier transform up at top. Let's see. Yes. Let's check this. Yeah, this is the sinc function. So we get that from rect. And then if you multiply rectangles multiple times, right? So you've got a rectangle here, convolved with another rectangle, all to infinity. You start out with a sinc function at the beginning. And since all we have to do is multiply these together, you'll end up getting more and more, the product more and more. And you'll end up seeing that this is, after 3, you get this very flat edge out here, very flat edge out here, and then you get this bell shape here. Now, this bell shape is of the Fourier transform of the f of x, but you can still build intuition off of this graph because you see these wiggles out on the left and the right end up becoming flat. So you lose, I guess, that information. So to summarize, we've got this sine, the sinc function that we multiplied many times. And if you take the inverse Fourier transform, the claim is that this will end up looking like a Gaussian. And that's a technical exercise that I will leave to you. Okay, so to revisit the origin of the Gaussian, what happens if you convolve a PDF infinitely many times? You'll end up getting a Gaussian for any PDF, so a PDF or any PDF. And then this is the central limit theorem. So why are Gaussians everywhere? You can think of the fact that physical phenomenon are outcomes from many random variables, and we often look at sums or averages. On cameras, for example, we look at the photon count over a time interval. And so you can consider that, you can use a model. So it's a model. Again, that's a key concept in this course. A model of images is to use light as photons. Right, so this is a perspective, right? So even though you'll end up just reading off a single pixel sensor value, which is technically a single individual random variable, that random variables oftentimes can be decomposed into a sum of random variables. And when it can be, that is when you see things as Gaussian. So you see this pixel intensity as a photon count. So a model of images as a photon count. Okay, whenever we have a sum, we've got the central limit theorem that kicks in, and we see that summing random variables is equivalent to convolving the PDFs. And this result applies to any random variable as long as they're independently summed. So thank you. In class, we did go over some questions that we are not going to go over in this video, which is a perk of showing up in person. But in the future, we will have the recording situation worked out so that our lecture videos will be uploaded as they were. Thank you.